All right, so today we're going to look at graphing quadratic functions in standard form. That's f of x equals ax squared plus bx plus c. That's the generalized form. So we're working out of the Great Minds, Module 4, Lesson 17. I'll leave it up there if you want to write your title in. All right, so a ball thrown in the air is represented by the function h of t equals negative 16t squared plus 96t plus 6. T is the time in seconds, and h is height in feet. So what does the domain represent? And remember, the domain is all x values that are true for a function. All right, so take a second to think about that. But the domain in this case is the time that the ball is in the air, right? Sorry, it's not working. Also, I'm using a pen because it's easier to see. In math, I always recommend using a pencil. Don't use a pen unless you're doing a live video. All right. What does range represent? The total height, right? Since h of t is the height in feet, our range would just be the height that it was actually thrown. So height in feet. Ball is above the ground. Okay. What height was the ball thrown at? So what was the initial height? So the initial height is when t equals 0. So let's look at the equation here, right? So if you think about when t is equal to 0, plug 0 in here. So this just becomes 0. Plug 0 in here, that becomes 0. 0 plus 0 is 6. So it was 6 feet. So that probably means that the guy who threw it was about 6 feet tall. All right, so after how many seconds does the ball hit the ground? How would we find that out? Well, it hits the ground when the height is 0, right? So we're going to set the equation equal to 0. And that should give us the height that it hits the ground. So there's a couple different methods to solve. You can, let's see, let me think about what's the easiest here. So you can complete the square, or you can use quadratic formula. So let's go ahead and we'll try completing the square because that's what we've been doing in previous lessons. Oh, sorry. Okay, h of t equals negative 16t squared plus 96t plus 6. All right, and so we know we're looking for when the height is, sorry, sometimes it goes out of focus when I write. So we're looking for when the height, this here, is 0. So we're finding our zeros, or our x-intercepts. So I'm actually going to subtract 6 from both sides. And the reason I'm going to do that is because now I'm going to complete the square. And before I complete the square, I actually want to pull out 16, I believe. Let me see here. Yeah, because we don't want, so we want the leading coefficient to be just be t squared. We want it to be 1 for when we complete the square. So I'm going to grab my calculator here. All right, so we know 96 divided by 16 is 6. So when we pull it out, we'll have, and I'm pulling out a negative. So negative 16. And then I'll have t squared. And since I pulled out a negative, 96 divided by negative 16 is negative 6 t. Okay. All right. And then I know that I'm going to be adding something to complete the square. So I'll get a different color here. Plus something to complete the square. Okay. And since we're adding something on this side, we need to make sure that we add it on this side as well. So plus, and since it's this number is technically multiplied by 16, so don't forget your 16. 16 times whatever number we add. All right. So let's see, half of 6 is 3. So we're going to be adding 3 squared. I'll go ahead and write it as 3 squared over there. And the reason I keep it as 3 squared is because then the first time when I go in to do my square, it looks like that, right? And then over here we can simplify it. So I'm actually going to plug this whole thing into my calculator. I'm going to go 16 times 9 minus 6 is 138. Okay, so here we have 138 equals negative 16 times t minus 3 squared. Now we're just going to solve. So first divide by negative 16. It's negative 8.625 equals interesting. Okay. I'm thinking about something here. I'm making sure I didn't do something wrong because we don't want to take a negative square root. Negative 6 minus. Ah, okay. I see where I went wrong here. I did one step wrong. Let me just double check real quick. Yep. All right. So in order to keep it, so since we added the number on this side, we actually have to subtract it on this side because we're not trying to change the equation. So if we added it to one thing, we have to subtract it from the other. Still. All right, so let's redo this here. This is not going to be 138. It's going to be negative 144 minus 6. Let's double check that that's right. Yeah. It'll be negative 150. This is why pencil's good for math. Mistakes happen. And they should. So the only reason I knew that was wrong too is because when I came down here and I looked at what would happen next, I knew I'd be taking the square root, right? And I know if I take the square root of a negative, sorry, it's blurry. I know that if I take the square root of a negative, I end up with an imaginary number. And I know that that's not right. We know that we're going to have real numbers because we know that the ball hits the ground at a specific time. So there will be zeros. So I knew that this was wrong. So let's see, what's this going to be now? It's negative 150 divided by negative 16. And 9.375, that's better. positive, so we're doing something right now. All right, so now I'll take the square root. Second square root, 9.375. Just doing it on my calculator. And we end up with plus or minus. And I'm going to approximate about 3.06 equals t minus 3. All right, so now we have to solve it twice, right? We're going to add 3. Add 3. And we're adding 3 to a positive and a negative. So we get t equals 3. 6.06 or negative 0.06. So we know that because the initial height, oh, sorry, scroll a little. Since we know the initial height was not 0, the x-intercept would go past the y. So this is not going to be included in our time. So that means that this is probably the time that it hit the ground. Well, it's definitely the time that it hit the ground. So hits ground at about, because remember we rounded, 6.06 seconds. All right, now we'll move on to the next bit here. All right, what is the maximum height and how long before it reaches it? So the maximum height is going to be at the vertex. And I'll go ahead and put our equation up here again. H of t equals negative 16 t squared. I'll double check. I think it was plus 96t plus 6. Okay. There we go. All right, so how will we find the maximum height or the vertex? Go ahead and think about it for a second. So we already completed the square earlier, but we did it on the other side. So I'm going to go ahead and complete the square again, just to do it. And the reason we're going to complete the square, is because that gives us, completing the square gives us the equation in vertex form, right? So let's go ahead and do that. So we have h of t equals negative 16 t squared minus 6t plus some number, plus 6 is out here, and then minus whatever that number is times 16. So we knew that it was 9 or 3 squared. So we end up with negative 16 t minus 3 squared. I believe it's minus 150. Oh, plus 150, sorry, because we subtracted it from the other side. That's right. So plus 150. Oh, and it's because this is negative 16. That's where I was going wrong. Okay, so I thought I made a mistake somewhere else earlier, but it's because I forgot that it was multiplied by negative 16. So that was the actual, that's where I got tripped up. All right. So this is the completed square form. And here we can see that the vertex would be 3, 150. So therefore the maximum height is 150. So therefore, those 3 dots mean therefore. (150 feet). Threw it pretty high. All right, what features are visible when the equation is presented in standard form? So just looking at it, up here, this is standard form. Okay, we can see quite a few things. We can pretty obviously see the position of the ball at t equals 0. So the initial height was 6. We can see that the graph will open down and have a maximum. Okay. Is anything else super obvious from this? All right. We know that we have a larger leading coefficient, so the graph will be more narrow. So more narrow than a typical x-squared graph. All right, so what would be visible in vertex form? So vertex form is what we found. I want to make it so you can see it. It's what we found right here. Well, obviously the vertex, right? Vertex or maximum. Super easy to spot. Also the end behavior, the leading coefficient still tells us that. Let's see, axis of symmetry, which is nice because then if you know any one point, you can find the other one because they're the same distance from it. And then also the end behavior, which I said, I just didn't write it down. End behavior, just like before. So they both tell us, it's like if you made a Venn diagram, you know, they would both tell us the end behavior. All right, time to graph it. What about our equation will help us create our, what about our equation in standard form will help us create our graph? And we just kind of went over that. The starting height, which we know time 0, the initial height was 6. Let's see, what else? Leading coefficients. So pretty much everything we just wrote. Can we factor to find zeros? Yes, we already found our zeros earlier, and we actually completed the square. We didn't factor. So yes. So we know that the first value that we found is not actually going to be on our graph. It's going to go past it because it was before our time, right? So I think it was, let me go back and look, it was some decimal. So negative 0.06 and 6.06. So for this, we're just going to say, we'll say negative 0.06, 0. And 6.06, 0. So this is the only one, or this is the only one that's on the graph. So not included in domain. And that's when we talked earlier about what the domain of this function tells us. It tells us what points are included in the domain. So that is not included in the domain, sorry. So what is the vertex and how did you find it? So we found the vertex by completing the square and putting our equation in vertex form. So found by completing the square and putting in vertex form. All right, and the vertex was, let's see, I just wrote it on the last page, I can't remember. 3, 150. All right. Now let's go ahead and put these key points on here. So we have 3 and then 150. That's our axis of symmetry there. And 150 is about right there. And I labeled it in increments of 21. And then this 1.5. Okay. And then we know that we have a point that extends past over here, negative 0.60. It won't be included, but it'll help us to draw the shape of the graph. And then we have one that's just past 6 and at 0. And then since we're not going to include this point, let's use our y-intercept, our starting height, which was 0, 6. So that'll be right about there. Right? So you can kind of see we have all the points we need now. Ball went up, hit 150 feet. And then that was the max, started to go down. Not the best parabola in the world, but you get the picture. All right, and we'll label this here. So labeling key points. So 0, 6. And I'll go ahead and put over here starting height. Right. 3, 150. Vertex or max height. So max height was 150 at time 3 seconds. And then down here we have, sorry, 6.060, which is time ball hit the ground. So we can see our domain here, right? It goes from 0 to 6.06. That's when it ended. And we can see our range is from 0, because it did, even though it started at 6 feet, it eventually did hit at 0. So 0 to 150 would be our range. So you can put that over here. Domain would be 0 less than or equal to x, less than or equal to 6.06. And our range is 0 less than or equal to y, less than or equal to 150. All right, that's it. We've graphed our function. And that's all I've got for you today. There's a few more examples in the text. I might come back on later and do them. But that was the initial, and then we're going to call it good.